Ultimately, in order to make use of hypothesis testing or the hypothesis testing framework, we need to be able to actually take the results of a hypothesis test and draw conclusions from those results, and then state the conclusions that we're drawing in a way that is useful to the subject area that we're actually working within, but also in a way that is statistically valid or supported by the evidence that we actually have. So in order to make use of these results that we can sort of work to build up to, we need to draw the conclusions, and those conclusions need to be interpreted. And interpretation of the conclusions of a hypothesis test is something that's not always immediately straightforward, and it's something that needs to be done carefully so that the results you're actually drawing, the conclusions you're actually drawing, are supported by evidence, and then any decisions that you make on the basis of those conclusions are well supported and sort of justified decisions to be made. So what are the conclusions that we can actually draw from a hypothesis test? There are two possible broad conclusions that we draw from our hypothesis tests. We can either reject the null hypothesis or we can fail to reject the null hypothesis. At the end of the day, we're always making one of those two choices. We're always concluding one of those two things. If we use p-values to draw these conclusions, then if p is less than alpha, where alpha is our level of significance, then we reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis there. Right? And so with the p-value technique, our point is always that we're comparing p to alpha, and we're seeing, is p less than alpha or is it greater than alpha? Okay? If we're going to be using critical values, then we end up checking our test statistic against these critical values. And if t, which is our test statistic or our realized test statistic, is more extreme than the critical value, then we reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis. So in particular, if t is less than sort of a lower critical value or it's greater than an upper critical value, then we're going to reject the null hypothesis in those cases, right? Otherwise, we'll fail to reject the null hypothesis. Whether we're using the lower or the upper is going to depend on the hypothesis that we're looking at. If it's a lower tail alternative, we use the lower. If it's an upper tail alternative, we use the upper. If it's a two-tail alternative, we have one at each side. So the conclusions that we draw are only ever drawn for a set or specific level of significance, right? We're not drawing these conclusions broadly speaking, but we're saying we reject the null hypothesis at some specific level of significance. If you change the level of significance, it's possible that your conclusion changes. And that's why you need to be selecting a level of significance that is relevant to the situation you're actually dealing with. Right? So if we reject the null hypothesis, then we also can use the language that the result is statistically significant, and specifically at the alpha level of significance, right? So we say we reject the null hypothesis, therefore this result is statistically significant at the alpha level of significance. And so if you see a statistically significant result, what that means is that there has been a null hypothesis that's been rejected at some level of significance. Okay. So if we fail to reject the null hypothesis, then we say that the result is not statistically significant. And so this language is exactly interchangeable. In a statistical context, if we say statistically significant, or sometimes just significant, right? If you have a significant result, that means a statistically significant result. Then what we're saying is that it crossed the alpha threshold, and it is sort of, the p-value is less than alpha, or the critical value is more extreme. So with those conclusions, how do we actually state this? How do we communicate? How do we interpret the conclusions that we're making, right? And so in order for us to accurately summarize the conclusions of this test, then we have to state the conclusions. And in order to do so, we should be stating the conclusions. We should be including any of the relevant information that we needed to draw those conclusions, and then also connect the conclusion to the context that we're dealing with here, right? And so this last part's critically important, where it's not good enough for us to just say we reject the null hypothesis. We need to convert that back into the language of the field that we're working in, right? The null hypothesis actually represents something about the real world. And so we need to be able to say, what is true about the world, or what do we think is true about the world, supported by the evidence that we have here, right? And so that connection back is going to be critically important for us. So we're either going to reject or fail to reject the null hypothesis at a specified level. We should include our test statistic or the p-value, depending on what's relevant. The drawn conclusion should then be stated in terms of the underlying scenario. Okay, and so that's actually connected back to what does the null hypothesis represent? And in order to connect to this context, we have to interpret the hypotheses based on what they're actually representing. And so anytime you want to state the conclusion of a hypothesis test, you should be thinking about these sort of 3 points here, right? You need to be stating, did you reject or did you not reject? Is it statistically significant or is it not? We have to provide the information that supports that, because this information is both useful for the conclusion, but it's also going to be useful, broadly speaking, for the individuals interpreting your conclusions. And then you need to be able to state what that means in terms of the actual underlying scenario. Okay, so we can walk through a couple of examples of doing this exactly. So if we imagine that we're running a medical study here and we are testing this new drug, right, to see if it's going to reduce cholesterol, the null hypothesis is that it has no effect on cholesterol. Right, so that's our null. There was an observed difference of 2.8 millimoles per liter, corresponding to a p-value of 0.008. Okay, researchers are wanting to use a significance level of 0.01. And so we have to think about, well, what's the evidence here? What are we actually suggesting? And the first thing to note is that we have our p-value of 0.008, significance level of 0.01. 0.008 is less than 0.01, and so we're going to be rejecting the null hypothesis, right? The null hypothesis is that there has no effect on cholesterol, and so if we reject that, then we conclude that there's evidence that this actually does have an effect on cholesterol. The observed average is going to correspond to this difference of 2.8 millimoles per liter. And so including a statement that has all of those components is going to be sort of what we want to do. And so, for example, we might say something like, because the p-value, which is 0.08, right, so we're providing the p-value here, is less than the level of significance, 0.01, we reject the null hypothesis, include that the data support the conclusion that the drug has an effect on cholesterol, right? So we've tied it back to the exact scenario here. Then we might want to provide some extra information here, right? So the mean reduction observed in the data is 2.8 millimoles per liter, which represents a statistically significant, because of the p-value, result at the 0.01 level of significance, right? And so this statement, it provides us with the information that we need to draw these conclusions, right? So our p-value, our level of significance. It's also giving us the test statistic, and we're stating, in terms of the scenario, we have to conclude that the drug actually does have an effect on the cholesterol, right? It's a statistically significant result. Take a look at another example here. So in this engineering study, we have this new type of steel alloy is being developed and compared to an existing alloy in terms of tensile strength. The null hypothesis is that the alloys have the same strength. The mean difference in strengths was negative 40 megapascals, corresponding to a test statistic of negative 1.8 with a t-based critical value at the alpha equals 0.05 of 2.09. Okay, so again, here we have our test statistic is this negative 40 value. The the average difference was this negative 40. Once we convert it to a test statistic, that's negative 1.98, and we're going to be comparing that to a value of 2.09. Now, if we note, our null hypothesis is that the alloys have the same strength, right? So the alternative is going to be that they have different strengths. Notice that this is a two-tailed test, and so this negative 1.98 value here is a value that we're actually going to want to be comparing, right? So 1.98 is a value that we're going to be comparing to the critical values, which are going to be plus and minus 2.09. Okay, and the reason it's going to be this plus and minus 2.09 is because this is a two-tail hypothesis test, right? And because we're saying that this is a t-based critical value, we know it's symmetric, and so we know that the positive value and the negative value are going to be our critical values. And so in particular, we have to ask, well, if we take sort of the interval negative 2.09 to 2.09, right? And we have a critical value of, or a test statistic of negative 1.98. Is negative 1.98 in this interval? And the answer is yes, it is, right? So because it's in that interval, we fail to reject the null hypothesis. And so because our critical value is less extreme, or is our test statistic is less extreme than our critical value, we fail to reject the null hypothesis at the alpha equals 0.05 level. Therefore, this is not a statistically significant result, right? And so if we want to start including all of this together, we can state something like this. Because the observed test statistic, which is negative 1.98, does not exceed the critical values in magnitude, as in negative 1.98 is not greater than negative 2.09, right, in terms of its magnitude. So it actually sits above it in terms of the negative. We fail to reject the null hypothesis. And then we have to sort of connect this back, right? So thus there is insufficient evidence to conclude that the two alloys differ in strength at the 5% level of significance. Okay? So that's our conclusion stated back in terms of the actual scenario. And we can state that the new alloy was 40 megapascals weaker on average. However, this is not a statistically significant result at the 0.05 level of significance, right? And so here we're noting that we failed to reject. We're noting what that actually means, that the two alloys do not differ in strength, right? We include the information, the negative 1.98 and our 40, and we're also noting that this is all at the 5% level of significance, right? So we have all of the information there. We could then use that conclusion to draw whatever conclusions or to make whatever decisions we need based on this scenario, okay? With these conclusions, we are either rejecting or failing to reject the null. We never accept the null. And this is worth just dwelling on for a second to think about why that's the case and to sort of understand that in some more depth. So we can never accept the null. The closest we get is failing to reject it, right? And the problem with this is that we're not actually assessing whether there is positive evidence in favor of the null. We're only looking to see if the data contradict it. We say, if the null hypothesis is true, how rare is this result that we're observing, which is not the same thing as saying how much do the data actually support the null. They're saying how much do they contradict the null, right? So in a sense, if we have a lack of evidence against a claim, if we don't find contradictory evidence, that is not often strong evidence for the claim, okay? Now, all of this hypothesis testing framework starts from the assumption that the null hypothesis is true, and then we look, is that actually the case? Okay, so we have sort of this assumption that the null is true, and we're looking to contradict this. If we think to, say, the criminal justice system, right, the assumption is always going to be that there's innocence, that you are not guilty, right? And then as a result, you're looking to prove that there is sort of this guilt. You're always looking to prove sort of some positive claim. In our case, right, we're starting from the assumption that the null hypothesis holds, that there is an assumption of innocence, and then we have to look and see if there's evidence that contradicts that, okay? The other way that you can sort of think through this about why accepting the null doesn't work is you can think about how there's likely alternative null hypotheses that we could have come up with that would have resulted in exactly the same conclusion. So what do I mean by this? Well, consider if we had tested the null hypothesis mu equals 0 or the null hypothesis mu is equal to 0.01, right? Only one of those could possibly be true, if either of them, right? But very likely, they're not going to lead to a significantly different test statistic, right? Because the observations we make that are in support of 0 are going to be similar to the observations made in support of 0.01, right? So if we imagine, for instance, observing sort of x bar equals to something like 0.05, right? Then we're halfway between these points. Any conclusion we make about mu equals 0 is also going to hold about mu equals 0.01, or almost certainly, depending on the test. And so in this case, the null hypothesis that we choose, if we had chosen to accept it, right? Well, what's the difference between accepting mu equals 0 and mu equals 0.01, right? And so we're not building up evidence in favor of this. We're just looking to see if there's evidence that contradicts it, okay? So the null hypothesis really needs to be chosen as a statement that we are willing to believe without affirmative evidence, right? It is sort of the statement that we're going to assume is true about the world, and then we look and see, does the evidence contradict that assumption, okay? So we make it to be conservative, and it's the default state of things. We don't need evidence to believe it. And if we've set the null up in this way, then there's really no difference between failing to reject it and accepting it, right? In that sense, we're going to be acting as though the null hypothesis is true because it's the thing that we're assuming without evidence, okay? And so in practice, when we fail to reject the null, we're going to treat the null as though it's true, right? And that's because we've selected a very good null hypothesis that is the statement we're willing to believe if we don't have any other evidence to the contrary, right? And so if you've chosen a good null hypothesis, then this fail to reject is not sort of a problem. It becomes a bigger issue if you choose a very bad null hypothesis and then you fail to reject it and then you act as though it is true. In that case, that's going to be sort of a riskier conclusion to be drawing, right? But if you're selecting a good null hypothesis, then at the end of the day, these two scenarios end up being practically quite similar, okay? In order to make practical use of hypothesis tests, we need to be able to draw and state our conclusions, right? A key component of this is going to be communicating the conclusions to individuals who are going to need to make decisions on the basis of those conclusions. But the other key component is that we work in sort of the land of statistics to draw conclusions from the data, but then we need to be able to take that and convert it back into whatever subject matter we're actually dealing with, right? And so we need to be able to say, how does this conclusion relate to the actual hypotheses that we're discussing, and how are those hypotheses sort of codified in the real world? Without that ability to connect back to the real world, then we're not going to be able to make effective decisions from our hypothesis test, and that's ultimately the goal of running these hypothesis tests in the first place.